Welcome back to the Deep Dive. It is Sunday, February 15th, 2026.
Good to be here. A lot to talk about.
Yeah, today we're doing something a little different. Usually we take a stack of articles, we float around the edges of a topic, maybe crack a few jokes about the state of the industry. But today, no. Today we are putting on the suit. Metaphorically speaking, of course.
Metaphorically, I am strictly in engineering casual today, as always. But the mindset is definitely buttoned up.
Right, because we're stepping into the role of a senior technical strategy consultant at a, let's say, a top-tier automotive engineering firm.
Okay, I like it.
And for the next hour, you, the listener, you are not just a subscriber, you are the client. You are the chief engineer. You're the technical director sitting at the head of a massive mahogany table staring down the barrel of a billion-dollar architecture decision for your, 2029 vehicle platform.
That's exactly the time frame, 2029 SOP. And we really have to set the stage here because the air in that room is very different now than it was just 2 years ago.
Oh, massively different.
I mean, if we look back at 2023, maybe early 2024, that was the gold rush.
Just get the EVs on the road. Whatever it takes.
Exactly. It was a pure panic for capacity, a race for who could put the biggest range number on a billboard. Engineering teams were, they were signing blank checks for silicon carbide capacity, didn't even care about the price, just to secure supply.
Right. The fear wasn't cost. The fear was getting left behind.
But here we are, February 2026. The party is over. The hangover has set in.
And the hangover is cost, with a capital C.
It's a ruthless tug of war. You've got the marketing department on one side, and they're still demanding extreme efficiency because, look, range anxiety is still a thing. Physics hasn't changed.
Still the #1 question people ask.
But on the other side of the rope, the finance department is demanding mass market cost structures. Because we're not just trying to sell EVs to people who buy Porsches anymore. We're trying to sell them to people who buy, Corollas.
The era of cost is no object. Engineering is dead and buried. You can't just throw the most expensive part at the problem and call it a day.
Which brings us to the entire premise of this strategic report. 2 years ago, if you asked a boardroom full of executives what the future of the traction inverter was, they would have all chorused in unison. All silicon carbide everywhere.
Oh, yeah. 1,200-volt SiC-based MOSFETs in the city hatchback, in the pickup truck, in the, the electric scooter.
And our job today, as your consultants, is to sit across that mahogany table and tell you that strategy is wrong.
Okay.
It was an oversimplification. I'd even say it was lazy engineering. The real innovation in 2026 isn't just about swapping material A for a better material B. It is all about precision optimization.
So we have a mission. We're delivering a strategic technology report. And you, being the consultant, have structured this properly, I assume.
Of course, we're doing this McKinsey-style, top-down communication, MECE principle that's mutually exclusive, collectively exhaustive.
No fluff.
No fluff. We are not going to waste your time. We're here to give you a decision-making framework.
Okay, lay out the executive summary for me. I'm the CEO. I've got 2 minutes between meetings. What's the pitch?
The core thesis is this. To survive and win in the 2026 market, OEMs absolutely must pivot from a brute force cynics approach to a strategy of precision. And we've broken this down into 3 strategic pillars.
Okay, pillar 1.
Pillar 1, architecture and device strategy. This is about moving beyond the all-SiC dogma. We're going to talk about hybrid switches and the real industrialization of gallium nitride.
Pillar 2.
Pillar 2 is the physical layer strategy. The chip is no longer the bottleneck, the package is. So we're talking about the now mandatory shift to sintering and some advanced chemical implementations in cooling that are just critical.
And the 3rd pillar.
Pillar 3 is the validation strategy, the shift left, how we move away from the massive bottleneck of the physical dyno and toward power hardware in the loop and active load technologies.
Architecture, physical layer, validation. Got it. Okay. Let's open the file. Pillar 1, the architecture pivot.
Right. Let's start with the problem statement. 800-volt architectures are, they're effectively standard now for anything in the premium segment. If you launch a premium car in 2026 without 800-volt fast charging, you are dead on arrival.
You're not even in the conversation. But the volume, the real money, the profit is in that $150K to $200K RMB range.
Yeah.
The $25,000 to $30,000 global car.
And that is precisely where the all-SiC strategy completely falls apart. Silicon carbide is the Ferrari of semiconductors. It's incredibly efficient, it handles voltage beautifully, but even with all the new capacity we've seen come online, it is still 2.5 to 3 times the cost of silicon per square millimeter of die.
And on the other side of the garage, you have the old, reliable IGBT, the silicon workhorse. It's cheap, it's robust, it's available from a dozen suppliers.
Yeah, but it's slow and it's lossy. The physics of the IGBT, it's a bipolar device, right? So when you turn it off, you have these things called minority carriers that get trapped in the drift region. They have to recombine.
And that takes time.
It takes time. And during that time, current is still flowing while the voltage across the switch is rising. That product of current and voltage is power loss. Pure heat. We call it the tail current. It's the Achilles heel of the IGBT.
So for years, the industry has been stuck in this very binary choice. You either pay for the Ferrari, the SARD chip, or you settle for the, the reliable but inefficient tractor, the IGBT.
Correct. But the big strategic unlock for 2026 isn't choosing one, it's choosing both. We are seeing the real emergence of what we call the hybrid switch paradigm.
Now, I really want to drill down on this because the word hybrid in engineering usually implies some sort of compromise. So you're telling me I am putting a silicon carbide MOSFET and a silicon IGBT in the same power module wired up in parallel.
That's exactly what I'm telling you.
That sounds like a complete thermal and electrical nightmare. I mean, they have different coefficients of thermal expansion, they have different gate threshold voltages, wildly different switching speeds. How on earth do you stop them from basically fighting each other to the death?
It's an arbitrage strategy. You're not treating them as equals, you're arbitraging the fundamental strengths of their physics. Think about a typical drive cycle. 90% of the time, you're just cruising. Relatively low load, low stress.
Okay, steady state.
But it's at 10%. The acceleration, the high-speed switching, that's when the stress happens. The SiC chip, you can think of it as the sprinter. It has zero tail current. It can turn on and off in literal nanoseconds.
Right.
The IGBT, on the other hand, is the weightlifter. It has a very low saturation voltage, VSAT, at high currents, so it loves to just sit there and carry the heavy load once it's on. It's more efficient in pure conduction.
So one is good at changing state, the other is good at holding state. How do you manage the handoff between the sprinter and the weightlifter? Because if you just turn them both on and off at the exact same time, the IGBT is still going to have that tail current loss.
Right.
You haven't solved anything.
Exactly. You are 100% correct. If you drive them synchronously, you gain absolutely nothing. The magic, and this is where the real IP is in the gate timing. The choreography. This is what companies like NXP have been refining for years.
Okay, walk me through it. Let's do a play-by-play. The microsecond timeline of a single turn-off event. Current is flowing through both devices.
Okay, visualize the current. Both chips are on, conducting in parallel. You want to stop the flow, step 1. You send the off signal from the gate driver to the IGBT only.
So the IGBT gate goes low, but the CMC gate stays high. It's still on.
Correct. Now, physically, the IGBT starts to shut down. Remember those minority carriers, the source of the tail current?
Yeah, they're trying to recombine and keep the current flowing.
Normally, that current would have to fight against the rising voltage across the switch, and that's what creates all the heat. But here, the 6th channel is still wide open. It's a super highway for electrons. So the current that was flowing through the IGBT simply shunts instantly over to the SiC MOSFET.
It takes the path of least resistance, like water flowing downhill.
Precisely. So the IGBT turns off under what we call zero voltage switching conditions. We're very close to it. There's no voltage spike across it as it turns off, which means there's virtually no switching loss. The dreaded tail current is completely eliminated because the current has an easy alternative path.
So now for a brief moment, all the current that was shared is now flowing entirely through the SiC chip.
For a few microseconds, maybe 5, maybe 10 microseconds, depending on the tuning. And then snap. The gate driver sends the off signal to the SiC MOSFET.
And because it's 6 MOSFET, it just cuts off instantly. Clean as a whistle, no tail.
Exactly. You've effectively used a small, fast, expensive SiC chip to clean up the messy turn-off behavior of a large, slow, cheap IGBT.
That's incredibly clever. But let me play devil's advocate here. I'm the chief engineer, and I'm looking at my driver board layout. I now need 2 independent, isolated gate drive channels for every single switch position in my inverter. I've just doubled my driver complexity.
You have. There's no free lunch. You have increased the complexity of the PCB and the control logic in the microcontroller, but you have to look at the total system cost.
Okay, make the case.
NXP's data on this, they have a reference design they call the 20 inverter analysis. It shows this precise timing strategy reduces the turn-on energy, or EON, by a staggering 80%, and the turn-off energy, EOF, by 40% compared to a pure IGBT solution.
80% reduction in turn-on energy. That's not an incremental gain.
No, it's a step change. You are getting performance that is very, very close to pure 6E. But here is the kicker, the part that makes a CFO happy. Because that 6G chip only has to handle the full current for a few microseconds at a time, it doesn't need to be rated for the full continuous thermal load of the motor.
Ah, so it doesn't need a huge die.
It can be tiny. You can use a SiC chip that's 1/3 or even 1/4 the size of a main inverter chip you'd use in a pure SiC design.
So you spend a little more on a smarter, more complex driver board to save a massive amount on the expensive semiconductor die area. That's the trade.
That is the trade. And for a mass market 400-volt or 800-volt vehicle in the 2026 to 2028 timeframe, this is the golden mean. It gets you the range without the bankruptcy.
Okay, so that covers the pragmatic, cost-down approach. But what about the other end of the spectrum? The high-performance challenger. We have to talk about gallium nitride, GaN.
We do.
I mean, we've been hearing GaN is coming for, what, a decade now? It's finally in my laptop charger. Is it actually ready for a 300-kilowatt traction inverter in a car?
It is arriving in 2026 prototypes, and it is an absolute beast. But it is a very different kind of beast than silicon carbide.
How so? What's the fundamental difference?
If SiC is the king of high voltage and high temperature, GaN is the king of raw electron mobility. It switches. It switches so fast, it's almost hard to comprehend. We're talking about switching losses that are, depending on the current, anywhere from 35 to 70% lower than SiC.
Wait, lower than silicon carbide? I thought 6 is the gold standard for efficiency.
It was. GaN is better. It's because the physical device capacitance is so incredibly low, it just doesn't hold on to charge. It can change its state from on to off almost instantaneously.
But I've always heard that speed kills. Or, in power electronics, speed breaks things.
Speed is the ultimate double-edged sword. When we talk about fast, the key metric is dV/dt, the change in voltage over the change in time.
Right.
A standard IGBT might switch at, say, 3 to 5 volts per nanosecond. A modern SiC MOSFET might do 10 or 15, maybe 20 on a good day.
And GaN.
GaN wants to switch at 100 volts per nanosecond or more.
100 volts per nanosecond.
Yeah.
That's not a switch anymore. That's a radio transmitter.
You've hit the nail on the head. That is the strategic risk. If you just drop a GaN-based inverter into a standard vehicle architecture, you will fail every single EMC electromagnetic compatibility test in the book. It's a nightmare.
What does that actually look like? What is the driver experience?
You'll have high-frequency common mode currents coupling into the low-voltage harness into the CAN bus. You'll hear a high-pitched whine on the AM radio. You'll get interference on the FM radio. You could even disrupt the LTE connection.
And what about the motor itself? I've seen what high dV/dt does to motor windings. It creates these reflected waves, and you get voltage doubling at the motor terminals.
It completely destroys the insulation. The partial discharge will eat away at it. And worse, it ruins the bearings. The high-frequency currents find a path to ground through the motor bearings, creating tiny electrical arcs that vaporize the grease. We call it EDM, or electrical discharge machining, and it pits the surfaces of the ball bearings until they fail.
So using GaN isn't just a simple component swap. It's not like changing a tire. It forces a complete redesign of the motor insulation system, the cable shielding, the filters on the inverter output.
Everything. And the protection has to be insanely fast, less than 1 microsecond. A GaN chip will literally vaporize itself in a short-circuit event before a standard fuse even knows that current is flowing. You need ultra-fast, intelligent, active protection built into the gate driver.
So why on earth would anyone do it if it's such a massive headache?
Because of another architectural innovation, the T-type topology. This is the other piece of the puzzle that makes GaN viable.
Okay, explain T-type for me.
Right. Standard inverters that we've used for decades are two-level. You have your 800-volt DC bus. You switch a device on, the motor sees 800 volts. You switch it off, it sees 0 volts. Simple. But to do that safely, you need a switch that's rated for 1200 volts to handle the voltage spikes.
And 1200-volt chips, as we've established, are very expensive.
Especially in GaN. T-type is a 3-level topology. It's a bit more complex, but it splits the voltage. It has an extra switch that connects the output to a neutral middle point. So instead of switching the full 800 volts across one device, you're only ever switching 400 volts across any given device in the string.
Which means You don't need 1200-volt chips. You can use 650-volt chips.
Exactly. And 650-volt GaN or SiC chips are practically commodity items. They're used in servers and solar. They're mature, high yield, and much, much cheaper than the specialized 1200-volt dies.
So the strategic takeaway for the chief engineer is, don't just look at the price of the chip, look at the topology. By using a smarter architecture like the T-type, I can use cheaper, more available chips to achieve the same 800-volt system output.
Correct. It's about using architecture to cheat the cost curve. It's brain-beating brute force.
Okay, this is a perfect transition. Let's move to pillar 2. We've got the muscle, the hybrid switches, the fast GaN devices. But all that muscle is completely useless without a brain to control it. Let's talk about the gate driver.
This is the component that's so often overlooked by executives, but for the engineers in the room, this is where all the magic is happening now. The gate driver is that critical interface between the low-voltage digital microcontroller and the high-voltage, high-power analog switch.
And traditionally, this is a pretty dumb component. You gave it a signal, it pushed voltage to the gate. You took the signal away, it pulled voltage from the gate. That's it.
It was entirely passive. You tuned its behavior with a soldering iron. You'd literally solder a tiny gate resistor onto the PCB. If you wanted to slow down the switching to pass a difficult EMI test, you'd have to solder on a bigger resistor.
But then you're stuck with that big, slow resistor for the entire life of the car.
For every operating condition. And a big resistor means slow switching, which means high switching losses, which means more heat. So you are always forced into a bad compromise. You had to sacrifice efficiency to buy yourself some safety margin and EMI compliance.
Enter the intelligent gate driver. You highlighted the NXP GD3162 specifically in the report. What's the big shift here?
The shift is to what we call dynamic gate strength. Instead of a fixed physical resistor, the driver chip has multiple internal current sources. It can push, say, 10 amps, 20 amps, or just trickle a single amp into the gate of the power device. And it can decide which one of those to use cycle by cycle.
That's the key, isn't it? The real-time cycle-by-cycle adjustment.
That's everything. Imagine you're driving on the highway at a steady speed. Cruise control is on, low torque demand. In that situation, peak efficiency isn't as critical as, say, electrical quietness. So the driver intelligently softens the gate. It slows down the switching just a little bit, reduces the high-frequency harmonics, the EMI.
So the AM radio is crystal clear, no interference.
Right. But then you slam on the accelerator to pass a truck, the current command spikes. The driver detects that high torque demand instantly, and in the very next switching cycle, it stiffens the gate. It drives it as hard and as fast as physically possible to minimize the switching time and thus the heat loss in the silicon.
It's like having active suspension for electrons. It's soft when you want comfort, which is low EMI, and it's stiff when you want performance, which is high efficiency.
That is the perfect analogy, and the data here is just compelling. NXP showed that by just implementing this dynamic drive strategy on a standard WLTP drive cycle, they reduced the total switching losses by 38%.
38%, with no change to the expensive silicon, just by being smarter about how you open and close the door.
That's it. It's pure intelligence.
I want to go back to the software knob for EMI, because as an engineer, failing an EMC test late in a program is my absolute worst nightmare. It means board spins. It means weeks, maybe months of delays.
It's the classic shift rate disaster. You find the problem at the very end when it's most expensive to fix. With a dynamic gate driver, if your validation team finds an unexpected noise spike at, say, 100 megahertz, you don't have to respin the board. You don't get out the soldering iron.
What do you do?
You go into the software calibration map and you say, okay, in this specific torque and speed range, slow the turn-on rising edge by 5%. You literally tune out the noise in code.
You're debugging a hardware problem with a software patch.
You can save millions in development costs and months of schedule. It's a revolution in the validation process.
Let's talk about another feature you flagged, active discharge. This touches on both safety and, critically, the bill of materials, the BPOM.
Right. Every EV has a huge DC link capacitor sitting across the battery terminals. It's a big bucket of energy. And if you get in a crash, that bucket can be holding 800 volts of lethal potential. It's a major hazard for first responders or mechanics. You have to be able to drain it safely and quickly.
And the traditional way to do that is a separate, dedicated circuit, a big bank of power resistors and a contactor or a MOSFET, to switch them in.
Correct. It's a brute force solution. It takes up a lot of valuable space on the PCB. It adds cost. It adds failure points. The GD3162 and similar drivers implement what's called active discharge using the motor itself.
How does that work?
It toggles the inverter's main power switches in a very specific controlled pattern that intentionally creates a short circuit through the motor windings, but in a way that doesn't create any net torque, so the car doesn't suddenly lurch forward or backward.
It effectively turns the motor's own copper windings into the discharge resistor.
Exactly. The energy in the capacitor is dissipated as heat in the motor in a matter of milliseconds. And for you, the chief engineer, here is the value proposition. You get to delete that entire discrete discharge circuit from your board. You save anywhere from $4 to $6 per inverter.
$5 in the automotive world is a fortune. People get promoted for saving 5 cents.
And it's not just the cost. You free up about 8.4 cubic centimeters of PCB space. In this modern power density war, that space is absolute gold. You can use it for more capacitance, better filtering, or just shrink the whole package.
One last thing on the driver before we move on, health monitoring. You mentioned this is the digital twin concept finally coming to life at the component level.
This is so critical for long-term reliability and warranty costs. The driver is physically connected to the CC chip's gate and FES. It can, with incredible precision, measure the on resistance, or ARDS on, every single time the switch turns on.
And the on resistance is like a vital sign for the chip. It goes up as the chip degrades.
Exactly. If a wire bond inside the module starts to crack from thermal fatigue or the solder layer underneath starts to delaminate, the electrical resistance spikes up. The driver sees this trend over millions of cycles. It can tell the vehicle control unit, hey, switch A in phase U is showing signs of aging. Its resistance is 15% higher than nominal. Let's limit the peak power to 80% and flash a service vehicle soon light on the dash.
True predictive maintenance. Instead of a catastrophic no-start failure on the side of the highway, the driver gets a warning 1,000 miles in advance.
It completely changes the liability and warranty cost equation for OEM.
Fantastic. Okay, moving on to pillar 3, the physical layer. The body. We can have the smartest brain and the fastest muscles, but if the bones and connective tissue fail, the whole system goes nowhere.
And this, I would argue, is the single biggest bottleneck in 2026. The chips have officially outpaced the packages. We're putting Formula One engines into, go-kart chassis, and the specific problem, the component that's failing, is solder.
Good old solder.
Ugh.
SAC 305, tin, silver, copper. We've used it for decades on every circuit board. Why is it suddenly failing us now in power modules?
It's just physics. Basic material science. Look at the melting point. Standard lead-free solder melts at roughly 217 degrees Celsius.
Okay.
Modern silicon carbide chips are now rated to operate at 175 degrees Celsius continuous junction temperature. Some are even pushing 200 degrees.
That is uncomfortably close. You're operating at over 80% of the material's melting point.
We have a term for this in metallurgy. It's the homologous temperature. It's the ratio of the operating temperature to the melting temperature measured in Kelvin. For solder at 175C, that ratio is about 0.85.
What does that mean in practical terms?
It means the metal is mechanically soft. It's like jello. It creeps, it deforms, it fatigues very, very quickly.
So every time the traffic light turns green, you accelerate, the chip gets hot and expands, you hit the red light, you stop, it cools down and contracts. And that solder layer in between is getting squished and stretched.
Over and over and over. And eventually the solder layer cracks. It is the #1 root cause of failure for high-power modules today, period.
So what's the solution? We can't just stop using solder, can we?
The solution is to get rid of it. The strategic shift is to sintering, specifically silver sintering.
Right.
Instead of melting a metal alloy to join the chip to the substrate, you take a paste filled with microscopic silver particles, apply pressure and heat, and the particles fuse together into a solid, pure silver bond. Now think about the melting point of pure silver. It's 962 degrees Celsius.
That's a completely different league. That's a blast furnace.
So now let's redo the math. Operating your chip at 175C, that's a homologous temperature of just 0.34, the silver doesn't even know it's hot. It is as solid and mechanically rigid as it is at room temperature.
What does that do to the reliability statistics? What's the real-world impact?
It's not an incremental improvement. It is a fundamental step change. Element Solutions, one of the leaders in this space, released data showing that switching from a high-end solder to a silver sinter paste improves the power cycling capability by a factor of 20x.
20 times, not 20%.
20 times, from maybe 20,000 cycles to failure to well over 400,000 cycles. You effectively remove the die-attach layer as a potential failure mode from the design. It will outlive the car.
But, and here's the chief engineer me speaking again, silver is expensive, and this isn't a simple drop-in. I can't use my existing reflow ovens. I need to buy new sintering presses. That's a huge CapEx investment.
It is CapEx, you're right. You need specialized presses that can apply 10 to 30 megapascals of pressure during the heating process. It is a completely different factory line, but let's look at the OpEx, the operating expense.
Okay, go on. I'm listening.
Sintering is a dry process, or at least a much cleaner one. Critically, you don't use flux.
And flux is nasty stuff. It's corrosive.
Right. If you use solder, you have to apply flux to clean the metal oxide so the solder will stick. Then, after reflow, you have this sticky, corrosive flux residue all over your expensive module, so you need a massive industrial washing machine to clean it off. Then you need a water treatment plant to handle the contaminated wastewater from that washer.
And sintering. It just removes that whole cleaning stroke.
It completely eliminates it. Element Solutions did a detailed total cost of ownership, a TCO analysis, for a 300,000 unit per year production line. And what they found was shocking. Even with the higher material cost of the silver paste and the amortization of the new presses, the total manufacturing cost per unit went down by 40%.
40%? How is that even possible?
Because you eliminated the entire cleaning line, the water treatment facility, all the floor space they took up, the chemicals, the labor, and the massive amount of energy required to run those cleaning systems. It is a classic counterintuitive win. You pay more for the advanced material to save a fortune on the manufacturing process.
Okay, that's a compelling case. Let's briefly touch on cooling before we leave the physical layer. You mentioned acidic coolant. That sounds absolutely terrifying.
It's a slow-burn chemical reality that a lot of teams are now waking up to. We all use these beautiful pin-fin heat sinks, copper or aluminum plates with thousands of tiny pins to maximize the surface area for heat transfer. And the coolant, a mixture of water and ethylene glycol, flows directly over them.
And glycol breaks down over time, right?
Under years of heat and stress, glycol degrades into various organic acids, glycolic acid, formic acid. The pH of your coolant drops. If you have a bare copper cooler, that acid just starts eating the copper. It creates corrosion debris, these little particles.
Which then gets swept downstream and clog up the tiny channels in the pin-fin structure.
And you get localized hot spots, which accelerates the degradation, and eventually you get thermal runaway and the inverter fails. The solution that's becoming standard in 2026 is advanced plating, specifically high phosphorus electroless nickel. The trade name from a company like Element Solutions is Niclad.
So it's like a barrier layer, a suit of armor for the copper.
It is a perfect amorphous suit of armor. They've tested it for over 1,000 hours in a hot, acidic salt spray chamber. Zero corrosion. For any OEM designing for a 15-year vehicle life, this kind of advanced plating is no longer optional. It's mandatory.
Okay, this brings us to our last major pillar, Pillar 4, the validation strategy. We've designed this beautiful advanced inverter. Now, how do we prove it works without going bankrupt or missing our launch date?
This is where the real culture war is happening inside a lot of OEMs. The old guard, they love the dyno, the dynamometer.
The dyno is the temple of automotive engineering. The noise, the smell of hot oil, the spinning shafts, the element of danger. It feels like real engineering.
It's visceral, absolutely. But it is also incredibly slow, phenomenally expensive, and genuinely dangerous. A high-powered dyno cell costs millions of dollars to build. It costs thousands of dollars a day just to run. And if you have a software bug that accidentally commands full torque at 0 speed...
You snap a multi-thousand-dollar shaft.
Yeah.
Or worse, a coupling explodes and sends shrapnel through the wall.
I have seen it happen. It is terrifying, and it can set a critical development program back by weeks or months. The 2026 strategy, the only winning strategy, is to shift left.
Meaning
you move the testing earlier in the timeline into the lab before the expensive, one-of-a-kind prototype motor even exists.
And this is where P-Hill comes in. Power hardware in the loop.
P-Hill. The concept is simple. You take your real physical inverter, the hardware, you put it on a bench in the lab. But instead of connecting its outputs to a real motor, you connect it to a motor emulator.
And a motor emulator is what? A giant programmable power amplifier.
That's a great way to think of it. It is a very high power, very fast electronic load that is programmed to mimic the physics of a motor perfectly. If your inverter pushes out 400 volts at a certain frequency, the emulator sucks up exactly the amount of current a real motor would. It simulates the inductance, the resistance, the back EMF, everything.
So as far as the inverter is concerned, it thinks it's driving a car down the road.
Exactly. But there's nothing spinning, the lab is silent, it's completely safe.
And because it's all based on a simulation model, you can do things you can never do in real life.
Now you're thinking like a validation strategist. You can test the active short circuit protection 1,000 times. You can test what happens if one of the motor cables is suddenly cut. You can simulate the motor overspeeding to 20,000 RPM. If you tried to do that on a real dyno, you would need a bomb shelter. On an emulator, you just hit reset on the computer.
Now, in the report, you mentioned a company called AVL and their active load technology. How does that fit in? Is it different from a full emulator?
It is. A full motor emulator is still quite expensive because it has to have incredibly high bandwidth to perfectly simulate things like torque ripple. AVL had the insight that for, say, 80% of inverter testing, long-term thermal tests, durability cycles, component aging, you don't need that perfect high-fidelity simulation. You just need to push the power through the device.
So the active load is the Goldilocks solution. Cheaper than a full emulator, but way smarter than just a passive resistor bank.
It's exactly the sweet spot. But the killer feature, the one that revolutionizes lab economics, is power recirculation.
Okay, explain that. Because my electricity bill for the R&D dyno lab is astronomical.
I'm sure it is. On a traditional dyno, you pull massive amounts of energy from the grid, you put it into your inverter and motor, and the dyno brake on the other end just turns it all into waste heat. You are literally paying to heat up the atmosphere.
Burning money.
With an active load system, the energy flows from the DC power supply through your inverter into the active load cabinet, and then the active load's internal electronics converts that AC power back to clean DC and pumps it back into the input of the DC supply.
It creates a closed loop.
It's a loop. You are only drawing power from the grid to cover the losses in the system, the efficiency delta. You can cut your lab's energy consumption by 90% or more.
And because it's all electronic and safe, with no moving parts, you can run lights-out validation. You set up a test script to run 500 consecutive WLTP drive cycles. You turn off the lights, lock the door, and you go home for the weekend. The robots run all night, all weekend.
That is how you hit a 2028 launch date in this environment.
It's the only way. If you are still waiting in line for dyno time in 2026, you have already lost.
We've covered the 4 pillars: architecture, brain, body, and validation. Now let's zoom out to the world map, part 5. The regional competitive landscape. Because it's clear that China, Europe, and North America are not building the same cars or using the same strategies.
Not at all. The priorities are distinct. Let's start with China. The key word, the obsession, is integration.
The X-in-1 powertrain.
Right. We're well past 3-in-1. We're seeing 8-in-1, 10-in-1, even 14-in-1 integrated powertrain units. They are combining the motor, inverter, reducer, the onboard charger, OBC, the DC-DC converter, the battery management system, BMS, and even the vehicle control unit, VCU, into a single physical block.
Why, though? Is it just a marketing gimmick to get a bigger number? It's all about cost and packaging. One single aluminum casting, one coolant loop, one set of high-voltage connectors. The incredible supply chain density they have in the Yangtze Delta region allows for this kind of tight integration. And, critically, they are the fastest to adopt the hybrid CCDT setups we discussed to hit the aggressive price points for their domestic mass market.
Okay, contrast that with Europe. What's the focus there?
Europe is playing the role of the guardian of reliability and increasingly sustainability. They are less focused on extreme X-in-1 integration and much more focused on things like sintering for long-term life, achieving ASIL-D functional safety standards, and improving the low-carbon footprint of their manufacturing processes.
The so-called green passport for the battery and now for the inverter as well.
Exactly. There's a willingness to pay a slight premium for a module that is proven to be more reliable, more repairable, and ultimately more recyclable. It's a different value system.
And finally, North America.
North America is the land of the pickup truck. The Cybertruck, the F-150 Lightning, the electric Silverado. The focus here is on raw peak performance, peak torque, towing capacity, hauling.
So they're the ones still buying the biggest, most expensive SiC chips.
They are. They're pushing the power density envelope with pure SiC. And the other big trend there is a heavy focus on cloud connectivity. Using the inverter as a rich data node for fleet diagnostics, they're thinking about predictive maintenance not just for one car, but for a commercial fleet of 10,000 delivery vans.
Okay, Mr. Consultant, we have gone deep. We've analyzed the architecture, the brain, the body, the validation process, and the competitive map. Now, I need the summary. I'm the chief engineer. My pen is hovering over my notebook. What are the 4 actionable recommendations I must take back to my team on Monday?
Okay, rapid fire. Recommendation 1, stop specifying all SiC by default. It's lazy and it's expensive. You must evaluate hybrid architectures and T-type topologies with GaN. You can get 95% of the performance for 70% of the cost if you're smart.
Recommendation 2.
Abandon solder for your power devices. If your inverter's power density is over 12 kilowatts per liter, solder is a massive liability. You must move to silver sintering. The TCO case is positive, and the reliability improvement is non-negotiable for future platforms.
Recommendation 3.
Digitalize your validation immediately. If your team is still relying primarily on physical dynos for development and tuning, you are too slow. You will be outmaneuvered. Invest in P-Hill and active loads to shift left and accelerate your timeline.
And final recommendation, number 4.
Embrace software-defined power. Use intelligent gate drivers like the GD3162. Start solving your EMI and efficiency trade-offs with software tuning in the lab, not with costly and slow hardware respins. Make it a software problem.
That is an incredibly clear and powerful roadmap.
It's a survival guide for the next 5 years of this industry.
Before we close out this session, one final provocative thought. A look over the horizon. We talked about smart drivers and software-defined power, but where does that trend really end? What's the next big leap?
I believe we are entering the age of the AI-first inverter.
AI, as in artificial intelligence in the power electronics.
Absolutely. Look at the new generation of automotive microcontrollers coming out, like the ST Stellar P series. They have dedicated neural network accelerators built right into the silicon.
What on earth does an inverter do with a neural network?
It creates virtual sensors. Right now, you pay for a physical temperature sensor to be embedded inside the power module. You pay for an expensive, high-precision resolver to measure the motor's rotor angle. These are costs, they're failure points.
Okay.
A properly trained AI model running on that MCU can infer the junction temperature of the SiC chip with incredible accuracy just by observing the real-time current, voltage, and switching behavior. It can infer the precise rotor position by listening to the magnetic noise and the current waveform.
So you literally delete the physical sensors from the bill of materials.
You delete the sensors, you delete the wiring harnesses, you delete the connectors.
Yeah.
The inverter stops being just a dumb power converter and becomes a true sensing and computing device that just happens to move electrons.
That is a fascinating future, and probably a terrifying one for the companies that manufacture resolvers and temperature sensors.
Disruption never sleeps.
On that note, we will wrap up this strategic session. To our client listeners, we hope this report has been valuable. Good luck with the 2029 platform decisions. Stay efficient and stay curious.